What we're going to look at this week is going to be similar to what we did last week, but that was the high level, how would I do this in practice and sort of day-to-day practice. But because the course has the word math in it, it behooves us to understand what was going on underneath that ODE 45 line that seemed to do everything for us magically. So we're going to write our own solvers this week that would do the same job as ODE 45 so you can see what the internals actually are there. Just a reminder of why we need these solvers at all. Anytime we have these kinds of equations here, which are nonlinear differential equations, if you look back to your notes for Math 225 or 232, whatever your actual differential equation course was, these things would not have been on your list of things you could solve. These are not linear. They're not constant coefficient. None of the tools that you learned in that class would apply to these equations. So you would be looking at them. And honestly, one of them comes up pretty easily. This is essentially the pendulum motion. Pendulum. So it's not like we have to look very far to find some exotic physical system that leads to this math. This is very easy to find. We can't solve them analytically. So to get any kind of prediction or simulation, we go to numerical methods. Weather is a huge font of things we can't solve, but we can predict, or at least find the rules for, and then use numerical simulations to predict them. Pharmacology. The key thing to keep in mind here, though, is that we are generating an approximation. So we're getting x of t or y of t, as our typical thing, equals. But we're not going to get it in that form. We're going to talk about this as we go through it. We're going to get it at certain time points, and we're going to have certain time values, and then an approximate y at that time value. And we're going to get vectors of those, exactly like ODE 45 gave us. But what's really there is actually a function. So the real answer is some honest-to-goodness, smooth graph thing that is x, let's call it y versus t. What we're going to get is going to be some numerical straight line kind of fudging close to the line that is the right solution. So just keep those two ideas in mind. The exact thing, a nice smooth curve that if I plugged it into the equation, it would satisfy the equation, versus our sort of blunt force, follow step, take step, and repeat until we get to the end of some simulation period. On the plus side, having spent last week looking at differential equation solvers, we know what we need. We need the rules of the game. We need a differential equation to make, otherwise what are we solving? We also need to know the starting point. So let me break this into pieces here. We're going to interpret this here as a formula for slopes. Okay? So we're going to do this in a very graphical sense. dy dt is a slope on the y versus t graph. And the idea is I can pick any point anywhere in here. If I pick a point, I can plug that t and y into my formula here, and it will spit me back a slope value that would make sense there. We're also going to need a starting point. So instead of just saying random points, let's start at some specific location, t naught, y naught, and by far the most common t naught value is 0. We start at time 0. And some time interval. So we're going to start at time 0, and because we have finite amount of time to simulate with, we're going to simulate to some final time tn. What that's going to look like when we get our solution is, okay, I started here, and then somehow I'm going to get a sketch of a curve, and I'm going to get to here. But because we don't actually have formulas to deal with, our solution's not going to look like a formula anyway. What we get are a series of points along the way. And if they're close enough together, we can connect those just with straight lines, and that would, roughly represent the solution that we're looking for. Let's get into how we're going to compute this then. First off, we're going to begin with the differential equation you've seen before. This is good old Newton's law of heating and cooling. And what it says is, remember here that f of t and y, function of t and y, is equal to dy dt. So when we say f here, we're interpreting it as a formula for the slopes of y. So slopes of y. T graph. And that happens to be equal to, on the other side, minus k y minus t environment. And all that is together, sorry, it's not just that part. These guys together say that the rate of temperature change is proportional to, is a constant times, proportional to a temperature difference. Notice this difference here. Temperature difference. We'll leave it at that. Our temperature difference, hey, I'm not the same temperature as my environment. I'm too hot. I'm hotter. Oh, then I'm going to cool down until I do match the temperature of my environment. And I'm going to do that at some kind of rate, and the rate's going to depend on surface area, heat capacity, thermal conductivity, all this other junk. But that all gets lumped into K. So the law that we're talking about here is very simple. It's if things are hot, they tend to cool down, and they cool down at a specific rate dictated by that formula. That's our input. So again, it's a formula for slopes on the graph, but it's something that we can interpret from the physics as well. When we run the solver, so then we plug this thing in. Notice F here goes into the solver. The solver does its magic. And then it gives us back two things, t and y. And I sketched that out earlier. T is going to be a vector. Y is going to be a vector. The first t is going to be 0. There's going to be a whole bunch more t's. And the last one is going to be our last time, whatever we said t end here was. Sorry, t end. And go to there. So we're going to get a bunch of predictions of time values and the temperature at that time. So then we're going to get y, we're going to call it y1, y2, down to y end here. So a prediction or a simulation of the temperature y at a sequence of time values. And with that, we can generate a graph, just like you did way back in week 1. Now we are getting the t's and y's from some exotic location, some exotic construction, but it's nothing different when it comes to interpreting it. Okay, so this is our goal. The idea is someone should be able to hand me f, and I should be able to build a vector of t's and a vector of y's. If you keep that in mind, these next few slides will make a lot more sense, and the code will make more sense. Our goal is to get a bunch of times and a bunch of y's so that we can build that graph right there.